Imagine a shirt that lends strength to your arms as you lift a heavy box, or a pair of leggings that helps your grandmother stand up from a chair. This isn't science fiction. It's the future being woven, thread by thread, in laboratories around the world. Welcome to G Fun Facts Online, where today we're exploring the dawn of wearable robotics, powered by a revolutionary technology known as fabric muscles. For decades, wearable robots, or exoskeletons, have meant rigid, bulky contraptions of metal and motors. They're heavy, noisy, and feel more like a cage than a second skin. But a paradigm shift is underway, moving from hard, external skeletons to soft, integrated muscular systems, driven by the development of smart textiles, fabrics that can sense, react, and move. So how did we get here? The journey to fabric muscles isn't a single path, but a convergence of three distinct streams of technology. First, you have the evolution of wearable robotics itself, starting in the mid-20th century with crude mechanical aids. By the 2000s, companies like Exobionics and Rewalk Robotics were making sophisticated exoskeletons for medical rehab. But the dream of a truly seamless, clothing-like device was still out of reach. At the same time, a quiet revolution was happening in materials science. This story really begins in 1880, when Wilhelm Röntgen, the discoverer of X-rays, noticed a rubber sheet deforming when he applied electricity. He had accidentally stumbled upon what we now call electroactive polymers, or EAPs. Progress was slow, but over the 20th century, new materials were discovered that could change shape in response to a stimulus. Then came shape memory alloys, or SMAs, unique metals that can remember a preset shape and return to it when heated. Researchers started weaving these fine SMA wires into fabrics to create things like low-crease cotton. The final piece of the puzzle was integrating these smart materials with one of humanity's oldest technologies, making textiles. In the early 90s, places like MIT began exploring smart apparel for the military. It was this fusion, advanced material science with traditional weaving and knitting, that unlocked the potential for actuators that were not just functional, but fabric-like. That convergence is the very essence of fabric muscles. Fabric muscles aren't a single technology. They're a diverse family of actuators. Let's break down the main types. First up are the electroactive polymer, or EAP, fabric muscles. These polymers change shape when you apply an electric field, which is why they're often called artificial muscles. There are a few kinds. Dielectric elastomers are like tiny deformable capacitors, a soft insulating membrane between two electrodes. Apply a high voltage, and the electrodes squeeze the membrane, making it expand in area. They can produce huge movements, but the downside is that high voltage means hundreds or thousands of volts, which is a big challenge for something you want to wear. Then there are ionic polymer metal composites. These use a low voltage, just a few volts, to make ions move inside a special membrane, causing it to bend. The low voltage is great for safety, but they produce less force and often need to be kept moist. Finally, there are conducting polymers, which also use low voltage and ion movement to change their volume. Swedish researchers have pioneered a cool method by coating regular cellulose yarn with an electroactive polymer. By weaving these coated yarns, they can create a textuator, a textile actuator that mimics the structure of natural muscle. The second major category is shape memory alloy, or SMA, fabric muscles. These are probably the most powerful type right now. The most common SMA is a nickel-titanium blend called nitinol. Below a certain temperature, the alloy is soft and easily deformable. Heat it up, and it snaps back to its rigid, pre-programmed austenite shape, generating a huge amount of force. In fabric muscles, this is done by weaving fine SMA wires into a textile and then heating them by passing an electric current through them. Researchers at the Korea Institute of Machinery and Materials have even developed an automated system to mass-produce fabric muscles from SMA coil yarn that's thinner than a human hair. A 10-gram actuator made this way can lift up to 15 kilograms. That's an incredible strength-to-weight ratio. Next, we have what might be the most accessible type, twisted and coiled polymer, or TCP, actuators. You can literally make these from nylon sewing thread or fishing line. You just twist a polymer fiber under a load until it coils into a spring. When you heat it, the fiber tries to shrink, but the coiling structure amplifies this effect, causing the whole structure to contract powerfully. These simple actuators can generate strains of over 20% and lift loads 100 times heavier than a human muscle of the same size. Their low cost and high energy density make them extremely promising. Lastly, there are fluidic fabric muscle sheets. This approach uses fluid pressure. Imagine a fabric sheet with an array of tiny, hollow, elastic tubes woven into it. When you pump a gas or a liquid into these tubes, the whole sheet is forced to change shape. By designing the textile pattern carefully, you can make it contract, squeeze, or bend in specific ways. These sheets are inherently soft, safe, and can achieve strains over 100%, while exerting forces more than 115 times their own weight. This makes them perfect for garments that need to apply pressure over a large area. So what can we actually do with these amazing fabrics? The most profound impact is in medicine and rehabilitation. For people with mobility issues from strokes, spinal cord injuries, or just aging, these soft robotic garments are a game changer. Researchers at ETH Zurich have developed the MyoShirt, a textile exomuscle that acts as an extra layer of muscle for your upper body. In trials, it increased a user's endurance by about 60%. There are also smart trousers being developed to help the elderly walk and avoid falls, and exoskeleton gloves that use fabric actuators to help patients regain their grip. Because they're portable and easy to use, these devices could allow patients to do therapy at home, increasing access to treatment. In the industrial world, fabric muscle exosuits can lift the burden on workers in physically demanding jobs. Imagine a work shirt that cuts muscle effort by over 40% when you're lifting boxes all day in a warehouse. A Korean team developed a wearable robot weighing less than 2 kilograms that supports the elbow, shoulder, and waist, reducing fatigue and the risk of injury without being cumbersome like traditional exoskeletons. And it's not just about strength. Fabric muscles are creating a new sense of touch in virtual reality. Full-body haptic suits like the Tesla suit use smart textiles to simulate physical sensations, making VR experiences for gaming or training feel incredibly real. Researchers are also using pneumatic fabric sleeves to create sensations of compression, skin stretch, and vibration on your arm, or fabric thimbles that let you feel the pressure and temperature of virtual objects. And of course, there's the future of fashion and sportswear. We already have smart fabrics that monitor heart rate, but the next step is active assistance. Imagine running shorts that help your stride, or a shirt that dynamically corrects your posture during a workout, or a jacket that can tighten to become more aerodynamic, or create air gaps for insulation, adapting to your activity on the fly. Despite this breakneck pace of innovation, we're not quite at the point of buying fabric muscles at the mall. There are still major challenges. The biggest is power. Powering these actuators with a small, lightweight battery that lasts all day is a huge engineering problem. Durability is another. Our clothes get worn, stretched, and washed. These smart fabrics need to be robust. This has spurred research into amazing self-healing materials, polymers that can autonomously repair themselves when cut or punctured, which could dramatically extend the life of these devices. Cost and scalability are also key. Many of these materials are expensive and made in labs. But automated weaving systems for SMA yarns and the use of cheap materials like nylon for TCP actuators are huge steps towards mass production. And finally, there is control. Making the fabric move is one thing. Making it move in perfect sync with the user's intent is incredibly complex. This requires a sophisticated network of sensors and advanced control algorithms. The future, however, looks even smarter. Researchers are exploring biodegradable actuators made from materials like gelatin, starch, or even seaweed, creating eco-friendly soft robotics. Artificial intelligence will be a game-changer for control, with machine learning algorithms that can learn and predict a user's movement intentions for more natural assistance. And the ultimate goal is a multifunctional, closed-loop system. The future trend is toward textiles that can not only actuate, but also sense and harvest energy. Researchers are developing yarns with built-in nanogenerators that capture energy from your body's movement to generate electricity. This could lead to self-powered smart textiles that finally solve the battery life problem. The development of fabric muscles marks a pivotal moment, a shift from the rigid and mechanical to the soft and integrated. We are on the cusp of an era where the boundary between human and machine blurs, not through invasive implants, but through the very clothes we wear. From helping a patient regain the use of their hand to giving a factory worker an invisible boost of strength, this technology promises to enhance our capabilities in the most seamless way imaginable. The threads of the future are being woven today, creating a world where our clothing becomes an active, intelligent partner in our lives.